I want to start today comparing the graphs of sine, cosine, and tangent. Which graph is graphed in blue? Cosine. Which one is in red? Which one do we see here in yellow? And then clearly the graph in purple is tangent. Now, we all know that tangent is sine divided by cosine. Well, we just got done, well, not just got done, we've actually been on trig for a while, but before trig we were studying rational functions, right? We were studying functions where the numerator and the denominator vary, and what happens when the numerator goes to 0, or the denominator goes to 0, or they both do, and all of those different things. So as you look at these graphs of sine and cosine, sine in red, cosine in blue, do you see any points where both of them equal 0 at the same time? No, never happens. So therefore, that proves right there, tangent cannot possibly have a hole in it. There's no holes, right? Holes are potentially when both the top and bottom of the fraction equal 0 at the same time. That never happens. Now, how frequently does cosine equal 0? Cosine being the bottom. Every pi. Right? Every pi. Okay? And every time cosine equals 0, what does sine equal?
1.
Either positive 1 or negative 1. What do you get when you have a function whose numerator is approaching either positive or negative 1, but the denominator is approaching 0? You get a vertical asymptote. So tangent has a vertical asymptote every time cosine is crossing the x-axis. It also happens to be every time sine is at a hill or a dip. Right? Now, what happens when sine approaches 0? What is cosine? Positive or negative 1. Well, what's 0 divided by positive 1 or 0 divided by negative 1? 0. So every time sine crosses the x-axis, what is tangent doing? It is crossing the x-axis. Okay? So there's a very, very close relationship between sine and cosine and tangent. And also, we talked about this briefly right before you left yesterday. But when we start graphing tangent by hand, right, what is the period of tangent? Pi. So the distance from this asymptote to this asymptote, because that's what one complete cycle is, right? Asymptote to asymptote is one cycle, and then that cycle just keeps repeating itself over and over and over again. The distance is pi. So the period of the tangent graph is pi. When we graph these by hand, I'm going to need you to accurately graph both vertical asymptotes, the point of inflection. By the way, the point of inflection is always halfway between the asymptotes. And then there is a point halfway between the point of inflection and the asymptote, pi fourths, that happens to have a really nice y-coordinate 1. I want to see you graph those points as well. So 5 important pieces of information for each cycle. 2 vertical asymptotes, a point of inflection, and then the 2 points in between, kind of like the quadrants, or quartiles. Okay? Well, what do those nice other points? So you've got your vertical asymptotes, those are every time cosine equals 0. You've got your point of inflection, that's every time sine equals 0. Those points in between happen to be whenever sine and cosine are equal distance away from the x-axis. So that'd be like right here, where sine and cosine cross. Because what do you get when you divide something by something of equal value? Positive 1. So you can see this point right here has a height of positive 1. That corresponds to this. So here's another point that has a height of positive 1. It corresponds to where they intersect there. But here's a height of negative 1. That's because this point here and this point here have the same value. They're only opposites of each other. What do you get when you divide something by its opposite? Negative 1. Okay? So that's how we're going to graph tangent. Now the cool thing about this is, when we graph tangent, we break each cycle into how many equal-sized chunks? 4. Same way we graph sine and cosine, right? Didn't we take a sine cycle and break it into 4 chunks? Same thing for tangent. We're going to break it into 4 equal-sized chunks. The only difference is tangent and sine have different periods, right? We're not going to take 2 pi and divide it by 4. We're going to take pi and divide it by 4. So the natural labeling of the x-axis that I would love to use every time is pi fourths. Clearly, if the period changes, if there's any horizontal squashing or stretching, I would need to adjust accordingly. Okay? So let's start by just graphing the parent function. Y equals tangent x. So get your graph paper ready, put some axes on there, and get ready to make some happy graphs. Okay. So first of all, I'm going to label the x-axis by pi fourths. Okay? Go through and put your vertical asymptotes. We've got vertical asymptote at pi halves. We've got 1 pi units away from that, 3 pi halves. Pi units away from that, 5 pi halves. Every odd multiple of pi halves is a vertical asymptote. Same place cosine crosses the x-axis. Then all of your multiples of pi are x-intercepts, or points of inflection. So negative pi, negative 2 pi, negative 3 pi, 1 pi, 2 pi, 3 pi, 4 pi, 5 pi, 0. And then we have a point pi fourths, comma 1, 5 pi fourths, comma 1, 9 pi fourths, comma 1, negative 3 pi fourths. And then we have negative pi fourths, negative 1, 3 pi fourths, negative 1, 7 pi fourths, negative 1. And that's it. There's all the important pieces. Now we just draw our tangent line squiggles. There you go, something like that. Beautiful. That's one of my favorite graphs. That is a happy graph. That's so annoying?
Yeah.
You're so annoying, man.
I know.
Why is that annoying?
Because how many things you have to make? That could be like 5 graphs in one.
It's the same number. That's the same as number of points when you draw sine and cosine.
I can do that. I didn't do 16 points.
Did you get full credit?
Yeah.
What are you complaining about? Okay. Make sense? Good. So let's graph some crazy transformations of this, shall we? Ready? Let's make one up. It's not too crazy. Let's go y equals 2 tangent x plus pi halves minus 1. How about that? Sound good? Sounds good. Get your graph paper, get your axes. Okay, so the first thing I'm going to do, analyze the period. So the period is what? Period is pi, so I would naturally like to label my x-axis by pi fourths. Can I label my x-axis by pi fourths and still plot all the points after stretching and shifting and everything on nice grid lines? Yes, that's what I'm going to do. Okay? Yeah, I'll take it. Thank you. Okay, there we go. Now these graphs can get very, very messy very quickly if you try to graph the parent and the helper graph and everything else, because all of these vertical asymptotes everywhere. So you're definitely going to want to use a different grid, different graph paper if you choose to graph helper graphs of any kind. Okay? So I'll provide those sheets to you again on this Friday's test. So we've got to choose, are we going to draw a helper graph or parent function on here, or do you think we can go straight to the final answer? First of all, let's go with the vertical asymptotes. The parent function has vertical asymptotes here, 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 there. What is the only transformation that's going to move these? Well, in general, what are the only transformations that can move your vertical asymptotes? Horizontal shifts and horizontal stretches and squashes. Okay? So if they're squashing in, you've got to be careful. What I typically do, if they're in the squash, I'll squash this first one in, and then I use the period and count to graph the rest, right? There is no horizontal stretching or squashing in this one, is there? No. So all I got to do is shift to the left pi halves. So let's take every one of these vertical asymptotes, shift it to the left pi halves. So we're actually going to end up with one right on the y-axis. And then that's it. I just got to go to the right pi, and that's going to be my next one. Go to the right pi from there. Go to the left pi. Okay, so there's the vertical asymptotes. Typically, there's a point on the parent function. There's usually a point right here at the origin. But when we vertically stretch that by 2, shift it to the left pi halves, and shift it down 1, it's going to be right here at negative pi halves, comma, negative 1. Right? Usually, on the parent function, there's a point right here at pi fourths 1. That's going to vertically stretch by 2. Shift to the left pi halves, and then shift down 1. So you're going to be right there at the point, negative pi fourths, comma, 1. Usually, the parent function has a point right here at negative pi fourths, comma, negative 1. That's going to vertically stretch by 2. Then shift to the left pi halves and shift down 1. So you're going to end up with a point right here. Okay? So let me just go ahead and draw one complete cycle here. Now I can use that and just repeat the pattern, and then halfway between there's going to be one here, and then here, and then here. Oop, that was bad. And so you end up with a graph that looks like that. Okay? Another reason I have you graph these extra points, the ones that are halfway between the point of inflection and the asymptote, because those points are going to show me that you vertically stretched it, right? Clearly, this point is usually 1 above the point of inflection. Now, because of the vertical stretching, it's 2. So you have to graph those additional points, because otherwise I won't know if you successfully, correctly vertically stretched or not. Does this make sense? Yes. Shall we do one more? Even nastier? Just gonna make it up. Y equals negative 1/2 tangent 1/3 x minus pi 6, and we won't do a vertical shift. Yeah, I'm going to make you do that one on your own because I don't want to try. No, I'm just teasing. All right. So what's our approach? First of all, what's the period of this graph? It is 3 pi. Okay, the period is 3 pi. That's vertically stretched by 3. Instead of being pi units apart, the asymptotes are going to be 3 pi units apart from each other. Okay? So not only is this being horizontally stretched, it's also being vertically squashed. So we're going to end up with some squiggles that are going to look like that. Well, maybe not like that, but they're going to be pretty bad. Okay? Well, the reality is, I'm actually going to graph it by labeling my x-axis, so I'm going to end up with squiggles that look like that. But if you actually graphed it in a nice aspect ratio, there are these really long, flattened out squiggles. This is a technical term for that shape, by the way. So naturally, I would like to label the x-axis by 3 pi fourths. But there's a horizontal shift. So let's factor that 1/3 out. So this is 1/2 tangent 1/3 x minus what? Pi halves. If I label my x-axis by 3 pi fourths, will I be able to nicely shift to the right pi halves? No. So do I say, I don't care, I'm going to do it anyway, and just eyeball that shift? You're going to have points not on the nice intersections of grid lines, which is totally okay. People did that in the quiz, and they got full credit. That was great. Or do we choose something that we can label it by that'll work? Can you think of anything we can label by that will give me points on the intersections of grid lines, but accommodate a period of 3 pi and a shift to the right pi halves? We just label by just straight pi fourths. I think that's a good approach. Okay, so let's label this pi fourths, there's pi halves, 3 pi fourths, pi, 5 pi fourths, 3 pi halves, 7 pi fourths, 2 pi, 9 pi fourths, 5 pi halves, 11 pi fourths, 3 pi. That's going to be one complete cycle from here to here. Right? Wicked. Okay. And I'm going to choose my y-axis to go up by halves. Good enough. All right. So for the parent function, there is typically a vertical asymptote right here. But what's going to happen to that? Because of the vertical stretch, it's going to stretch to where? Or sorry, did I say vertical stretch? Sorry. There's a horizontal stretch, isn't there? There's a horizontal stretch by how much? 3. So if I horizontally stretch this whole thing out by 3, where is this vertical asymptote going to end up? 3 pi halves. Okay? But then I also have to shift it to the right pi halves, so where is it going to end up after that? 2 pi. So after horizontally stretching by 3, then shifting to the right pi halves, that vertical asymptote right there is going to end up right here at 2 pi. And you should easily be able to check that. If you actually plug 2 pi in, you should get an undefined. Okay? So now, how far apart are all of the vertical asymptotes? 3 pi, the period. So my next one's going to be over here. Wow. Crazy. I can't fit anymore. That's beautiful. All right. Typically, your parent function goes through the point 0, 0. We got to reflect that in the x-axis, horizontally squash it by 2, horizontally stretch it by 3, and then shift it to the right pi half. Boom, pi half 0. Very nice. That's my favorite point in the world to transform the origin. Stretches, reflections, do nothing. All you do is shift it. Okay? Your parent function usually has a point at pi fourths, comma 1. We squash that by 2, reflect it in the x-axis, horizontally stretch it by 3, and then shift it to the right pi half. So you should end up with a point at 5 pi fourths, comma negative 1/2. And it should end up, is it guaranteed to end up halfway between the asymptote and the point of inflection? Yeah. So I'm guessing, based on the pattern I'm noticing here, there's going to be a point. Come on, pen. Your stuff's working. Sweet. Right here. Okay? I think that's correct. Usually there's a point pi fourths negative 1. vertically swash by 2, reflect, horizontal stretch by 3, shift to the right by half. That's kind of neat. It stretches out to here and then the shift moves right back. It's pretty cool. So yeah, that's great. Did my pen come back yet? What's going on? Let's see, can I draw this with my mouse?
Oh.
Not bad! Why did my pen stop working? Oh no, acetone. I got it this time. Good enough, alright. So then we'll have point here, something like that. Think a point here, something like that. That was beautiful. All right. Same. I'm just going to repost last night's homework. I think it ends up when you only do the tangent problems, it ends up being like 6 total problems. That's it.
No, there's more than that.
No, there's not. You have to look.
I was doing it last night.
T-A-N.
Yeah.
T-A-N.
Yeah.
So there's like 6 to 10 problems.
There's about 14.
Somebody else count who knows how to count. Make sure you do a good job. Total fair game to be collected tomorrow. Come in with some questions. How many times have I said that? Not collected. One.
You collected it.
Every day. Okay? Come in with good tangent graph questions. Tomorrow, we will learn how to graph reciprocals, so you'll leave